There's a lot of connectivity between astronomy and because celestial navigation. Yeah. The old wooden sailing ships they have used the sky until there's observatory like the U.S. has the U.S. Naval Observatory. You see, I can move it really easily. It probably weighs 5 tons from here on.
Wait.
I'll let you do it in a second, okay?
Come here.
But you can move it to any place in the sky by releasing the clamps here and moving it around. And then, do you know why we do that? Why we have to move the telescope?
Where do you get to?
It's a big white sun.
That's the sun. That is the sun, yes. Good job, Cameron. All right.
It's a prism.
So, yeah, there's a tube sticking up out of the roof here. Looks kind of like a Q-tip. I don't know if you saw it coming up. That's what's sending the sunlight down into the building here. And we're splitting it. We're taking 3 different light paths. That's because the sun is so bright, we get so much light from it, we can look at it in a number of different ways. So we have this sort of visual light path here, which is just if you look at the sun with your eye, that's what you would see. Don't do that, you go blind. So don't look at the sun. But we get some information.
I don't want to do
Look at it. Alright, so we can see the sunspots there on the surface of the sun. We'll get to those more later. We'll talk about what exactly is going on there. But we don't want to look at the sun just like that. There's lots of information that we can get from the sun if we look at it in some other ways. So one of the ways we look at it, we send it down through this light path here and into this box here. In here, there's a grating, a prism that splits the light out and makes a rainbow. And you say, well, okay, it's a rainbow, so what? But what's in the rainbow there? The spectrum of light. There are lines, there are blank spots, there are holes in the rainbow of light. And this is true even when we see in the sky. They're hard to see, but when we project it like this, we can see it. So there's these little black lines coming down. If you get closer there, you can see those. And what those are absorption lines. So the elements that are in the sun, they actually block the light at a very specific wavelength of light. And what we can do is we can look at that and say, oh, okay, this line here, right here, this blocking out, this line means that there's calcium in the sun. This one means there's sodium. This one means there's iron and carbon. We can't go and get a chunk of the sun and bring it back down to the lab and break it apart and figure out what's in it. But by looking at this light, at the spectrum, and the line, we can see exactly what the sun is made of. So about 125 years ago, there was a problem with chemistry. They had built a periodic table. It was great and wonderful, but there was a problem because they had number 1, hydrogen. Number 2, what? Nothing, blank. Right. That's what I'm saying. But yeah, they didn't know what it was there. They couldn't find it on Earth, but we found it in the sun. Astronomers did. We don't let chemists forget that we found helium. Helium, it comes from the word helios for sun. So helium is the sun element. It's actually very rare on Earth. And there's a shortage of helium. It's running out. Because every bit of helium we've used on the Earth escapes out of the atmosphere. It's so light. Yes, it probably will be pretty soon. It'll be very, very expensive in the next 10 years or so. So, helium So by looking at the sun like this, and we can use this with other stars too, we can look across the galaxy at other stars and see what they're made of. It's mostly the same stuff, but there's differences. We can actually tell how old the sun is from this information, and a lot of other things. So very useful. But sort of the opposite of an absorption spectrum, so that's what this is. We're looking at the lines that are absorbing light. There are emissions of light as well. And that's what's this third way. And it's sending it down through a filter. We're blocking out all the light except a particular wavelength of light. We're looking at hydrogen alpha. It's going into this camera here, and you see it up on the screen there. Actually, let me move this around a little bit so we can see. See, the same sunspot that's up there, we actually see more information. So like this part coming down here, you can't see that up there at all. So we get more information by looking at a different layer of the sun. And you can see, oh, it's actually coming real clear now. There's this cellular structure. You see all this sort of like, looks like lines, sort of like cracks in the sun. Those are actually convective cells. There's a better picture of it here in the black and white. You can look at that on the way out. But that is the plasma in the sun rising to the surface, cooling off and falling back down. You get the cycle, this convective cycle of heated plasma coming up and then falling back down. But sometimes that gets disrupted. You have magnetic lines in the sun that they get tangled up and they actually impede or stop this convective cycle. And that's how we form sunspots. So what's happening there is that the sunspot, the magnetic field lines disrupt the convective cell. So it stays up on top too long and cools off. It gets down to about 1,000 degrees cooler than the sun around it. The sun's about 5,500 degrees Kelvin, that's about 4,500 degrees Kelvin. So there's a substantial difference in temperature. It's still really hot, but this convective cycle getting interrupted by the magnetic lines causes this sort of cooling effect. Equator than it does up in the north or south regions. So the Earth sort of, it turns all in one. The sun doesn't do that. It wraps itself up. It has these magnetic lines and they get all tangled up. So about 150 years ago, they're putting the first telegraph lines down in the US.